transmission of cyclic redundancy check. As the developing of digital, we have growing demand and dependency on digital system, and the reliability of digital transmission becomes an important indicator in the digital communication system. On the one hand, redundancy check can give exam and control of the digital error. We can improve the efficiency of the equipment and the stability of the communication channel. On the other hand, it can improve to veracity and integrity of digital transmission. Redundancy check is a kind of algorithm that can be used comprehensively in the engineering domain. The CRC code can be divided into types. First one is serial CRC code. Serial CRC circuit is easy, but the delay time is longer than the other one. That will be introduced later, so the encoding time is lengthened and directly cause the limitation of application. The other one is parallel CRC, which has significant shorter delay time compared with serial CRC code. In this article, the principle of parallel CRC and the implementation of CRC decoder will be introduced. First, we recall parity check. What's the parity check? Parity check uses parity bits to check that data is being transmitted accurately. The parity bit is added to every data until data are transmitted. The parity bit for each unit is set so that all bits have either an odd number or an even number of set bits. What's shortage of the parity check? The shortage of the parity check is obviously. First of all, its probability of detection of the error is only about 15%, which means only 15% errors can be detected. In addition, each transmission would require a byte to be attached to a parity bit, and this process would have a great impact on the transmission efficiency. Now we move to the introduction of CRC. CRC is a linear code from the sub-branch from the main application. It's a binary code word. Coding is quite easy. The process of CRC can be described clear and briefly as follows. Assume the data sequence S1 of key bits such as B0, B1 to BK-1 is sent to a receiver R by a transmitter T. Meanwhile, the receiver R is permitted to check possible errors on the base data another sequence S2 of m bits B0, B1 to Bm-1, which is also produced by transmitter T. In this situation, the sequence S2 is generally considered to be frame check sequence. In fact, FCS can be generated when considering the feature of the complete sequence. For example, S1 S equal to S1 union S2, which is dissectable by some predetermined sequence P, P0, P1, P2, Pm of m plus 1 bits. The complete sequence S equal to S1 union S2 is got by connecting S1 and S2. After S is sent to R by T, R passes S through P, and the way of dividing is the application of the same special arithmetic after the message is obtained. If the arithmetical applement does not exist, it is proved that R has no error. In computing, a linear feedback shift register is the most basic standard block structure in an internal test circuit, used as generating past random numbers. Screens, both hardware and software implementation of a linear feedback shift register are common. An anti-order LFSR consists of n flip-flops and a number of XOR gates. In practical applications, meaningful two types of LFSR, which are XOR external linear feedback shift register and XOR internal linear feedback shift register, where G0, G1, G2 to Gn is 0 or 1. Q1, Q2, Q3, Qn is as LFSR output. The check code generator of CRC is obtained by division. So we can associate CRC with LFSR, which generate check code. Assume that the original information polynomial is mx, the generating polynomial is gx. Then the CRC code is mx times x, the root of r, divided gx. We can use the LFSR circuit to achievement. Move mx to the left by r bits in the circuit. This means that when enter the information code, then enters R0. Figure 3 shows the circuit. Now let's move to design of CRC code generation and the verification process. We can get a method of CRC code transmission process, then using ruijie description of generation module and check modular design CRC check modular, such as follow fig file. The whole process of the generation of CRC can be described as follows. Input 12 bits valid information code by state, and in the situation which CLK is as racing age and the load signal is 1, the cyclic redundancy check code would start generate check code, then add it to a 12-bit information code. After transmit this code to the receiving terminal, the check process is not run itself automatically, but requires a specific environment, which CLK continues. Its racing age status and handshake inputs answer is 1. The receiving terminal will receive a 7-bit information code with 5-bit check code. The next step is the use of the calculation of this 17 bits plus 5 bits code, which is finally 12-bit digital, and then discards the 12-bit code word from the last 5-bit check code. The 5-bit check code is the code word to be accepted. After those upper steps, using the received 12-bit code word divide the generator polynomial if the remainder from last step is equal to the check code. It means the code is correct. And if the final remainder is not equal to the check code, that means the check is failed and the code is not correct. Using shifter register is quite hard to implement the CRC calculations when used with high-speed serial data. Therefore, when we design the CRC circuits, the principle and the implementation of parallel CRC computing was designed. Here is a step of tilt, so I will not introduce. According above calculation, we can get 8-bit parallel competency RC16 logical relationship. We can look here. So, according the above table, it's easy to implement 8-bit parallel of CRC hardware circuit. We can use to CRC circuit parallel arithmetic to get a VHDL. In the program, we need to set the input and the output. Here is the detail. Now we move to the next steps. First, assume that the data stream of input terminal is 100101110. Next, have an observation of this coding simulation of wave sequence diagrams. By the wave diagram, we can get the CRC's check code is 101111110001. We can be seen from the follow figure. The use of parallel computing, which can be completed 8-bit date calculation within a clock pulse. If the use of serial computing, which only complete a bit operation within a clock cycle, through the above description, the speed of serial computation is only 1/8 of the parallel computation. The CRC check code is added to the input data stream and then make the output, and then the data stream is shown as follow: 1001001110010011000110001, and the tail is shown as figure 11. And then after 3 clock cycle period calculation, CRC will show as 00000000000000000. So that the code transmission makes no mistakes. So in this paper, I introduced some basic background of FPGA, CRC, and the method which CRC used to make the check process. We studied a parallel CRC algorithm, which through the principle of CRC check code analysis. At the same time, we can find that parallel CRC algorithm is quite complex with serial CRC algorithm, but the running speed greatly improved. The results of my study are promising. The method in FPGA or CRC has a significant ability of error check, but not that accurate. Further studies can be conducted for more precise and in-depth evaluation. The CRC method can only achieve error-free to accept, which means it just approximates market as error-free, but not guarantee reliable transmissions. To overcome this problem, a new method or development of CRC may be needed. So this is my presentation. Thank you.